Hey everyone, welcome back to the Midnight Developer Workshop series. This is episode 2, and today we are looking at the Compact Playground, a browser-based tool that lets you write and compile compact smart contracts without installing anything on your machine. By the end of this session, you will know how it works under the hood, how to deploy your own instance, and how to integrate it into your documentation. Let's get started. Before we dive into the playground, let's make sure we are all clear on what Compact actually is. Compact is Midnight Smart Contract language. If you have written TypeScript before, you're going to feel right at home. The syntax is very similar. But here's where everything gets interesting. When you compile Compact code, it doesn't produce bytecode like Solidity does. It produces zero-knowledge circuits. That means your contract logic can execute with full privacy. Private state, witnesses, shielded computation are all built into the language itself. So Compact is language, and the Compact playground is where we are going to write and test it today, right in the browser. No local setup required. So here's the problem we are solving. Setting up the Compact compiler locally, compactc, is not trivial. You need to download the right binary for your platform, configure your paths, manage versions as the language evolves. And if you just want to try Compact for the first time, this is not that easy. That's a lot of friction before you can even write your first line of code. This is especially painful for newcomers. Someone hears about Midnight, wants to see what Compact looks like, and they hit a wall of setup before they can even experiment. We needed something better. The Compact Playground puts the compiler in the cloud. You open a URL in your browser, write Compact code in an editable code block, press Ctrl Enter, and you get instant feedback. If there's an error, you get structured messages with line numbers and character positions, not raw compiler dumps. No download, no install, no path configurations. Just open and code. That's the entire value proposition. Let's look at how this all fits together. The architecture is refreshingly simple. Your browser sends a post request to a Hono server. The server takes your code, writes it to a temp file, and invokes the compactc compiler running inside the Docker container. The compiler outputs get parsed into structured JSON, and that JSON comes back to your browser. That's it. Browser to server, server to compiler, compiler back to browser. 3 hops, and you've got your results. The compiler runs with the skip zk flag, which means it does full syntax and type checking without generating the actual zero-knowledge circuits. This makes compilation fast. We are talking seconds, not minutes. Let me hit the key features quickly. First, editable code blocks. The code in your browser is fully editable with syntax highlighting and keyboard shortcuts. Second, there's a REST API, so any tool or editor can call the compiler. You are not locked into the web UI. Third, and this is a big one, MD book integration. You can drop the playgrounds, JS, and CSS into any MD book, and every Compact code block automatically gets a run button. This is how the Learn Compact book works. And fourth, rate limiting at 20 requests per minute per IP to keep things fair. The API is minimal, just 2 endpoints. Health tells you if the server is running and if the compiler binary is available. And compile takes your Compact code as JSON and returns the compilation results. That's intentionally simple. You can call this from a curl, from Postman, from a VS Code extension, from a CA pipeline. Anywhere you can make an HTTP request. We will use both of these in the hands-on section. Here's the best part. You can try this right now. The playground is deployed on Railway at compact playground app railway app. No login, no account, no sign up. Just open that URL and start writing compact code. If you're following along with this workshop, go ahead and open it in another tab. You can experiment as we go through these slides. This is an open source community tool, MIT license. It was built specifically to power the interactive examples in the Learn Compact book. That's the MD book-based tutorial for learning the compact language. It is listed in the Midnight Awesome the Apps collection alongside other community tools. And you can deploy it yourself, either with Docker for your own infrastructure or directly to Railway with a couple of clicks. All right, that's the overview. You know what it does, why it exists, and how it's architected. Now let's go deeper and look at how each piece works under the hood. Okay, let's go deeper and look at what's actually happening inside this tool. The backend is built on Hono, which is a lightweight Node.js web framework with essentially zero dependencies. If you have used Express, it's the same idea but faster and leaner. Parse is enabled out of the box, so browsers can call the API directly. Rate limiting is implemented in memory, 20 requests per minute per IP address, with automatic cleanup of stale entries so memory doesn't grow forever. The server runs on port 8080 by default, but you can change that with the port environment variable. Railway set this automatically when you deploy. When you hit the compile endpoint, your code goes through 6 stages. Let me walk you through each one. First, input validation. The server checks that you have sent a JSON body with the code field and that the code isn't bigger than 100 kilobytes. Second, rate limiting. Your IP gets checked against the in-memory counter. If you have exceeded 20 requests in the last minute, you get a 429 back. Third, file creation. The server creates a unique temp directory using an ID and writes your code to a .compact file inside it. Fourth, the compiler, compactc, runs with the skip setk flag on the temp file. There's a 30 seconds timeout. If the compiler hangs, the process gets killed. Fifth, output parsing, the raw compiler output, which is meant for humans, get parsed into structured error objects with file path, line numbers, and character positions. And sixth, the JSON response goes back to your browser, and temp directory gets cleaned up regardless of success or failure. Here's a nice quality of life feature. When you write a circuit in the playground, you don't have to include the pragma and import lines every time. The server auto-wraps your code. So if you write export circuit adds, the server prepends pragma language version and import compact standard library before sending it to the compiler. You just write the interesting part, and the boilerplate gets handled for you. But if you have already included a pragma, meaning you have written a complete program, the server detects that and sends your code through unchanged. So it's smart about when to wrap and when not to. The wrapping logic is driven by a snippet detection, and it handles 4 cases. If your code contains pragma, it's a complete program, sent to the compiler as is, no wrapping. If it has export circuit, it's a circuit snippet, gets wrapped with the pragma and standard library import. If it has export ledger, it's a ledger definition, same wrapping treatment. And if none of those patterns match, the server assumes it's a bare expression and wrap it inside a test circuit. This is great for quick experiments. You can just type an expression and see if it's a valid compact. Let's talk about how the server actually talks to the compactc. It is invoked as a child process. Nothing fancy, just an execution file with the right arguments. The skip setk flag is key. It tells the compiler to do all the syntax and type checking, but skip the actual zero-knowledge circuit generation. This makes compilation fast enough for interactive use. You get results in seconds instead of minutes. There's a 30 seconds timeout. If the compiler process doesn't finish in that window, it gets killed. This prevents any single request from hogging resources. And there's a nice fallback. If the compactc binary isn't installed, the server caches the end-to-end error and returns a clear message saying the compiler isn't available, rather than crashing. In production, the compiler runs inside the Docker container. The error parser is one of the most important pieces. The raw output from compactc is meant for terminal display. It's got ANSI colors, multi-line, stack traces, all that. Not great for programmatic consumption. So the parser structure error objects. Each error gets a file path, a line number, a character position, and a descriptive message. It recognizes syntax errors, type mismatches, undefined reference, all the common patterns. And there's a deduplication step. The compiler sometimes emits the same error multiple times in slightly different forms. The parser catches that and gives you a clean, deduplicated list. The frontend is a self-contained JavaScript class called compactc. When it initializes, it scans the page for code blocks and enhances them with editing and compilation capabilities. The code blocks use content editable, so there's real editable divs, not text areas. This gives you the proper syntax highlighting and formatting while still being editable. Control-Enter is the compile shortcut. You press it, your code gets sent to the server, and the result appears right below the code block. No page reload, no form submission. And a small but important detail, the tab key inserts two spaces instead of switching focus to the next element. Little things like that make the difference between a toy and a tool. Each code block gets two buttons, run and copy, with clean SVG icons. The run button triggers compilations, and copy puts the code on your clipboard. Status feedback is visual. When compilation succeeds, the code block gets a green border. When there's an error, it turns red. And while the request is in flight, you see a gray pulsing animation. So you always know exactly what state things are in without reading any text. Let's look at what the API actually returns. Both success and error responses follow a consistent JSON structure. On success, you get success true, an output field with a compilation message, and a warning array that might be empty. On error, you get success false and an errors array. Each error object has a line number and a message describing what went wrong. Type mismatches, undefined variables, syntax errors. They all follow the same format. This consistency makes it easy to build tools on top of the API. You always check success, then look at either output or errors. If you're writing documentation with MDBook, integrating the playground is 4 steps. Step 1. Copy compact playground JS and compact playground CSS in your MDBook project. Step 2. Add both files to your book TOML under the output HTML section as additional JS and CSS. Step 3. Use the compact language identifier in your fence code blocks. So triple backtick compact instead of triple backtick TypeScript. Step 4. There's no step 4. The JavaScript automatically finds all code blocks with a compact language tag and adds a run button. No extra markup, no special divs, nothing. It just works. This is exactly how the Learn Compact books work. Every interactive code example in that book is powered by this same playground. The Docker build uses a two-stage process. The first stage installs all the dependencies and builds the project. The second stage creates a minimal production image with just a runtime, no dev dependencies, no build tools, just what you need to serve requests. Building it is one command, docker build compact playground, and running it is just docker run compact playground. Hit the health endpoint to verify it's working, and you are done. Your own private compact compiler service. Security is handled through multiple layers. And this is important because you're running a public compiler service. Code size is capped at 100 kilobytes. Nobody needs to compile 100 kilobytes of compact code in one request. So this prevents abuse. There's a 30 seconds compilations timeout. If someone submits code that makes the compiler spin, intentionally or not, it gets killed after half a minute. Each compilation runs in its own temp directory with an ID name. This gets cleaned up automatically after compilations finish, success or failure. So there's no state leaking between requests. And of course, the rate limiting we already discussed, 20 requests per minute per IP. All of these together make it safe to run as a public service without worrying about someone abusing it. All right, that's the deep dive. You now understand every moving part. Let's put it all together and let's go into the practice. All right, time to get our hands dirty. Open up your terminal and let's start using this thing for real. For this hands-on section, you need three things. A browser. Any modern browser will do for accessing the live playground. Docker, if you want to build and run your own instance locally. And curl or Postman for hitting the API from the command line. If you just got the browser, that's fine for most of what we are about to do. Okay, let's start with the first demo, which is about health check. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to terminal. Okay, let's start with the second demo, which is about compile a circuit. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to the terminal. Okay, let's continue with the third demo, which is about a counter contract. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to the terminal. Okay, let's continue with the fourth demo, which is about triggers errors. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to the terminal. Okay, let's continue with the fifth demo, which is about clone and explore. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to the terminal. Okay, let's continue with the sixth demo, which is about Docker build. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to terminal. Okay, let's continue with the seventh demo, which is about progressive complexity. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to the terminal. Okay, let's continue with the eighth demo, which is empty book setup. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to the terminal. Okay, let's continue with the ninth demo, which is custom integration. In this slide, you can see a brief summary of what we are about to do. Okay, let's switch to the terminal. Alright, let's recap what we covered today. We learned what the Compact Playground is, a browser-based compiler service for compact smart contracts. We went through the architecture, Hono server, Docker-based compiler, structured JSON responses. We explored the compile pipeline, snippet detection, code wrapping, and the error parser. In the hands-on section, we hit the health endpoint, compile circuit of increasing complexity, trigger and read structure errors, clone the repo, build our own Docker instance, set up an MD book integration, and wrote a custom API integration. Thanks for watching. Drop questions in the comments and I will get back to you. And if you're following along, go build something. Fork the playground. Integrate it into your docs. Write some compacts. You've got everything you need now. See you in episode 3.